with continuation of such activities, it will build an environment of academic research as well as interaction between different fields. And my special thanks to Professor Abdurrahman Al-Hussein, as well as the best and meticulous organizer, Dr. Reem Al-Hefti, and also my mentor, Professor Abdurrahman Al-Goiz. I'm always indebted to him. I'm given the task from where Professor Hela left. I will continue, inshallah. Professor Hela introduced very nicely, mashallah, the smooth manifolds. And also she has seen that. Also, yes, also she has introduced algebraic structures such as a ring of smooth functions at a point, as well as tangent space and cotangent space. Roughly speaking, what is a smooth manifold is, you make pieces of Rn and take some pieces and glue them by smooth maps. Those are transition functions. The object so formed is called n-dimensional smooth manifold. It is smooth in the sense for functions you can differentiate, as well as you are able to do many things at that point. Manifold is a beautiful object. It lies.
Assalamu alaikum, Dr. Sharif.
Alaykum assalam.
How are you? Thank you for your kind words. Doctor, can you share please the file with us? Because the online students can't see the file right now.
شير ساوند محمد، شير ساوند يسار فوق بنفس الصفحة دي. ايوه يسار تحت.
Okay, thank you. Now it is appearing. Thank you very much.
Yes, so the manifolds are objects built out of open pieces of Rn, glued together by smooth maps. And some of the objects you can imagine, some of them are beyond imagination. They're abstract spaces. Important thing associated to a manifold, that at each point you have a ring of smooth functions denoted by C infinity P, as well as you have the algebra of smooth functions, C infinity M. These were the things we have, she has already discussed, Professor Hela. Today, and most important object we are going to introduce, that is, to each manifold M, there is associated another manifold, smooth manifold, Tm, that is called the tangent bundle. That is called the tangent bundle. So what is a tangent bundle? So a tangent bundle is defined, as you have the manifold, and at each point you have the tangent space. Now what you do is you collect all tangent spaces, form their union, and this is called the tangent bundle. Tm, union of all tangent spaces, is called the tangent bundle. Now what happens is, given a tangent bundle, you can express it as, because a point in the tangent bundle is a point from the manifold as well as a tangent vector at that. So the tangent bundle can be thought of as this thing. That is, Tm is set of all order pairs P, XP, where P is a point from manifold and XP is the tangent vector. Set of all this is the tangent bundle. And therefore, you have natural projection. You have natural projection. This is the tangent bundle. P is in manifold. XP is in corresponding tangent space. You have natural projection on the manifold. This projection says P XP equal to point P. This tangent bundle turns out to be a smooth manifold in the following way. Now what we do, we topologize tangent bundle by quotient topology, requiring the projection map to be a quotient map. So what we do, we take a chart here with local coordinates x1, xn, m being n-dimensional smooth manifold. Then inverse image of U you define a map phi from this inverse image. This phi is from U to Rn. This capital phi you define from phi inverse U to R to M. How it is defined? Phi at a point here. Point here is PXP. To use these coordinates, and other n coordinates, y1, yn, they are defined like this. Yi at that point, PXP is nothing but differential of local coordinates at P operating on XP. So these are the ones. So what coordinates you have? You have here xn, y1, yn, 2n coordinates, where xi's are nothing but, these xi's are nothing but xi circle phi. Xi operating at PXP is given by this, and yi are nothing but dx. So this way, Tm tangent bundle becomes 2n-dimensional smooth manifold. I hope it is clear. Right? Tangent bundle is there. Is that clear with the ideas? I think this one. This one. Yeah. Yeah. Fortunately, you talked about such a manifold which is parallel. By the this one. So it's tangent bundle. TS1. So you have only one coordinate here. You have only, well, because it's one dimensional, right? And on tangent bundle, I mean, you have PS1 is nothing but what? P XP. P in S1 and XP in PS1. PS1 is nothing but R. TPS. Now, what is your phi? You take a chart here, U phi. So phi will be from pi inverse U, that is in tangent bundle of S1 to R2. How it is defined? Phi of a point here, PXP. The first is nothing but X1P, and second one is nothing but DX1. These are this gives you the coordinates, two coordinates on the tangent bundle of the sector. That is speaking, you have a smooth n-dimensional tangent bundle is 2 n-dimensional smooth manifold. And the differential structure we have constructed, it turns out that, so here, I have explained the remark 4 in the lecture. This is what I have explained. The theorem says the natural projection map, that is phi from tangent bundle to M, given by phi of PXP equal to P, is a smooth map, and it is onto. And by virtue of that, it is a submersion. What is it? A submersion. Professor Hela introduced these three notions: immersion, submersion, diffeomorphism. These things were introduced back then. So here, this map is a submersion. Once you know that it is submersion, what happens by implicit, and there is implicit function theorem comes into play here, which we take a point P here. This is onto submersion. You will see that by inverse of singleton P is TPS, tangent space. And because this is a submersion, this is a smooth manifold of dimension of Tm minus dimension of M. That is, each tangent space is a smooth manifold of dimension N. And this is very natural also, because tangent spaces are isomorphic to Rn. And Rn has a smooth structure. You can borrow that smooth structure using that isomorphism in the tangent space, which makes tangent space itself as an n-dimensional smooth manifold. So,
if you take M to be just an open subset of Rn,
yes,
what would be Tn? I think
same.
simplify.
It is same.
It will be U cross
Look,
Rn.
this is U, Rn,
Open,
right?
which is open.
Yes. So the tangent bundle of U will be, of course, U cross R, because it is trivial bundle.
So it's trivial one,
But-
so it's easy to understand this point.
Yeah. Yes, but not in general true. For S1, it is true, fortunately. But S1, S3, they are parametric. You can factor them, but not in general. For example, S2, this does not happen. So each fiber tangent space is an n-dimensional smooth manifold. Next, if you have two manifolds, and there is a smooth map. This smooth map induces a smooth map on tangent bundle level. This is denoted by this. Now, how is this defined? Df, a point here, Pxp, equal to f of p dfpxp. And using differentiable structures of these two, it can be shown that this map is also smooth.
What is DFT? I know, but
Yeah, this differential of f at p, she has introduced it. Professor Hela has introduced it. Tangent space level. Each smooth function from one manifold to another manifold gives a linear map from TPM to TFPM. And its definition was that, which you said that you had some concerns, which we'll discuss, inshallah, after the lecture. Then that map is smooth. This is theorem 7. There is an exercise. A strong and curious student always checks whether he has understood the contents by verifying solutions of exercises. So there are a couple of exercises here, simple exercises. First exercise, show that tangent bundle of Rn is R2n, Rn cross Rn, as he suggested, as he said. Second is an interesting one, the tangent bundle of sphere. Please read it and try to solve it. And if you have any questions in it, my email can be found and you can discuss with me if you are stuck where at some place in the
have tutorial session today.
Myself, it's not possible for me. My age does not allow to stand more than 2 hours. Okay, all right, subhanallah. But tangent bundle is a tool which we are going to use for a very important notion. And that notion is the next section, that is vector fields. You know, smooth manifolds, as all the analyst people who are sitting here, they know that doing global analysis, especially partial differential equations, and even hydrodynamics, and theory of relativity, all these subjects, they need smooth vector fields. Vector fields on manifold, they are essential in studying differential equations, especially differential equations. So now, what is a smooth vector field? Again, I need to come here. You have the tangent bundle. Now, we are looking at a smooth map in opposite direction. A smooth map. Because both are manifolds, so we can talk of smooth map. From where to where? Manifold to tangent bundle. Such that, what happens? Say here is XP, which will be some P UP. Pi should send it back to P. Your X and pi should be such that so it is sort of reverse map to projection. So smooth vector field is a smooth map from manifold to tangent bundle, such that phi brings it back to the same position. This is also called smooth section of the tangent bundle. So if you look at the situation, this is X of M. X, M sits here in tangent bundle. So this smooth section of this is a requirement for the smooth section of the bundle. So a smooth section of the tangent bundle is a smooth map from manifold to the tangent bundle, such that pi brings it back to the same position. Such a smooth map is called smooth vector field. What is the name of it? Okay.
So requiring that just X, P to just a vector and T, PM is not enough.
Not enough. It should bring back to the same place. That is the requirement for smooth vector field. Now, what is the outcome of this? Outcome of this is that X at point P should be in TT. That is the requirement. X of P should be, XP should be a tangent vector in TPM. So this is the definition of smooth vector field. What is it? Smooth map from manifold to the tangent bundle. There is another consideration.
Under which condition we have this pi x equal to the horizontal? Is there a condition?
This is that. This is sharp. That is definition, right? Maybe I didn't understand your question. Go ahead.
We call it smooth manifold.
Smooth section of the tangent bundle, section of the tangent bundle, right? Now, the beauty of vector field is the following. Suppose you have a smooth manifold and X is a smooth vector field. Now, what you do, we take a smooth function. We take a smooth function in the manifold and define
Assalamu alaikum.
wa alaikum assalam.
Sorry to disturb you. Could anybody please fix the camera on the board to can follow you? Thank you very much.
دكتور وداد تابع. You can continue.
هلا دكتور يعطيك العافية. ما احنا قادرين نشوف صراحة البورد يعني الكاميرا.
شوفي قولي لي. يعني كذا.
لو عفوا ترفعها شوي دكتور.
Back, little back.
No, we did yesterday.
ايوه كذا نوعا ما كويس. الله يعطيك العافية.
يمين واليسار موجودة. أنا أروح يمين واليسار.
شكرا جزيلا. لا خلاص مضبوطة كذا. شكرا يعطيك العافية.
So we have a smooth vector field satisfying this definition. I took a smooth function in the on the manifold, and I'm defining something called X of F. It's a I'm defining it from manifold to R. And the definition is like this. XF at a point P to be equal to XP, you know, is a tangent vector operating on F. This is a real number because tangent vector operating on a function is a real number. So this is a well-defined function. A smooth function, a smooth vector field acts on a function to give you a real valued function XF defined this way. And it is easy to prove that this is smooth.
What's the definition of that? Is it the Lie derivative? Or
Sorry?
is it the Lie derivative, this one?
No, the tangent vector. She has defined, Professor Hela. Tangent vector is a map from C infinity P to R, satisfying linearity and derivation. No, it is the definition of tangent vector. Let me repeat. A tangent vector XP is a map from a ring of smooth functions to R, satisfying two conditions, linearity, XP of lambda F plus mu P to be equal to lambda times XPF plus mu times XPG. And second is the derivation, the ring derivation, FG to be equal to FP XPG plus XPFG. This one.
My question is that if I give you a smooth vector field, how could you define it? These are properties, how could you define it?
So these are not property. A map from C infinity P to R is said to be a tangent vector
If it satisfies,
satisfies these two properties. That is linear with respect to reals.
but if I give you X,
You
That's more
give me
vector.
X. Need not be always
if I
tangent.
give you an example, how could you define this X? It's just.
You mean this? It-
Like XP,
This, you are giving me a vector field.
yeah, concrete one,
Yes.
example.
Now, yeah, and a vector field, for example, trivial space Rn. Take the coordinate vector field, not tangent vector.
For example, del.
Yes, yes, del by del x. For example, on Rn, you have, say, first coordinate, is globally defined, and you have this as a vector field. This is a vector field, which at a point is a tangent vector, because the definition of vector field, right?
Fixed. Yeah.
Is that clear?
Yeah.
Now, what I am going to derive is the following. You started with this abstract definition of vector field, and we are using this abstract definition of vector field. For each smooth function, X acts on F to give you another function from manifold to R defined this way. And using smoothness condition, requirement for smoothness using chart, you can prove that this function is smooth.
Why is it different from the Lie derivative?
Now, Lie derivative is more general. I mean, sorry, vector field is more general. Lie derivative is restricted. And Lie derivative not only acts on functions, it acts on tensor fields also.
No, if I take a smooth field like what you said, and they want to define the Lie derivative Lx and
I'm
function,
coming to that. It is, you will see as a property soon.
it's the same.
Yes, you will come to it, inshallah.
Because I don't feel comfortable until I.
Yes, you will see, inshallah, as a property soon. But let me complete this. No problem. So what happens? You have a smooth vector field satisfying this definition. What happens? For each smooth function, you have a smooth function. And therefore, X is now a map from C infinity M to C infinity M. Please understand, not ring. This is global for C infinity M. Because for a function, you have shown that XF is in C infinity M. So given vector field, it acts as a map from C infinity M to C infinity M. The algebra of smooth functions, right? C infinity M. Now, because it uses definition of tangent vector, and tangent vector satisfies those two things: linearity with respect to real coefficients and derivation this. So this smooth vector field brings you a map from C infinity M to C infinity M, satisfying such two conditions. First condition what? X of lambda F plus mu G to be equal to lambda mu in real numbers. And derivation, that is X acting on the product is equal to XF product G plus F times product. So a smooth vector field with this definition as a section of tangent bundle gives you the derivation of ring of smooth functions. Conversely, given a derivation of a ring of smooth function or algebra of smooth functions, you recover the vector field. These two things are equivalent. These two things are equivalent. So there is an example of the vector field here. That is example 11, as actually was asked by Professor Abdul Rahman. Here, you take a chart, U being open subset, U being open subset of M itself is a smooth manifold, and you have local coordinate system, and that gives you tangent vector at each point del by del xi, and then you define the vector fields del by del xi. Then what happens is that
Just put F inside.
sorry,
So F goes inside.
yes, yes. So locally, every vector field can be expressed as the summation of xi del by del xi. This is a local expression, of course. Set of vector fields. We have seen what is a vector field. Satisfying what? This is the definition of vector field, and it is equivalent to, this is equivalent to this, what? X as a derivation of algebra of smooth functions. Satisfying those two conditions, X of lambda F plus and derivation. Ring. Now you collect all vector fields, set of vector fields, and you denote it by chi m to be set of all x such that you define addition of two vector fields. because vector field at each point gives you tangent vector. So you borrowed addition from tangent space on this. So here you have this addition of two vector fields. That is, if you have x, y vector fields, you defined x plus y at P to be nothing but sum of tangents, which is well defined in the tangent space. This belongs to. Addition is borrowed from tangent spaces. And also, one smooth function and x, you define the left multiplication. So this gives you vector field again. So what do you see here is that this XM set of vector field is left module. What is it? Over C infinity. Best example to algebraize while they defined module theory was this. This remark 13 I have already discussed, that two definitions of vector fields are equivalent. And that is the content of the proposition 14. If M is an n-dimensional smooth manifold, then X can be taken a vector X as a ring derivation, then X is a smooth vector field.
Here, why you call it left?
Because the
Left
left
multiplication,
multiplication.
Why left? Because the result is independent on left or right.
No, right doesn't work. Because XF
is real.
XF is not a vector field anymore. It is a function. We have just seen.
But here, FP of FP is real. No?
Yes. Yes.
Let's see why.
It's a tangent vector now. But here it is a vector field. And only left multiplication. Right multiplication is غير ممكن. Are you getting it?
By definition,
I want to interchange between FP and XP on the right hand side. He said you can just write XP, FP.
No, but here it is on the left. That is this is important, not that.
I said if you just
But here also it is a tangent vector. It also has a tendency of operating on functions. This is a real number. You cannot put here, otherwise that will be 0. Are you getting me? Tangent vector of a real number will be 0. Okay. So it is a left module. And as I said, some people in algebra wrote that this was the best example to be algebraized of left module over a ring of smooth functions. Okay, so theorem 15 is that. Now, we'll not stop here. Set of smooth vector fields, not only left module, it becomes Lie algebra. What it becomes? We are going to define yet another product on. I hope I'm carrying the concept with all of you. It's better engage. If you have questions, please, your questions are welcome. Because the purpose of lectures is to introduce the subject, and I hope that.
what do you write here in 2I? Is this properties or
I introduce vector field like this first, right? And then using this definition, we introduce X as a derivation. Yes, we use this as a definition, right?
Okay.
And using this definition, we have shown that X vector field acts on a smooth function to give you another smooth function.
Yes.
So that becomes a map from C infinity M to C infinity, satisfying these conditions. And these two are equivalent. That is what I wrote here. These two are equivalent.
This direction is easy, but that
The
direction,
first one is linearity. That's problem. And the second is
Derivation. Derivation. It's called a derivation in algebra language. Okay. Okay. What
but
is,
that direction is easy.
yes.
But that
This direction is also not difficult. What is required is to prove smoothness. Using this, you can define X from M to that, satisfying XF at point P to be XP of F.
same one.
Yes, and yes, and then you show that it's a smooth. So you get a map from X to, and that is the content here.
Yeah.
Uh,
Understand.
Yes. Now, as we have seen that it is a left module, it doesn't stop here. It becomes Lie algebra, as we have one more operation that is a product defined on XM.
I call that module.
Yes, please engage in
I
discussion.
don't
If you-
think they know module.
they don't want to know module, you mean? It's better to know. Because look, there is nothing like different subjects. All of them, they come together.
Yeah,
Mathematics is a good mathematics. So if you want to be a mathematician, you should have basic algebra, basic analysis, basic differential geometry, all these things.
That's why you have this one.
Yeah, and that's why we have this heat. Yes. Now, what I said is, please remember this is applicable definition. This is abstract one. This is applicable. So for us, a vector field is that object which acts on smooth function to give again smooth function. Now, what we do,
But they want to know the module.
that model theory should consult basic
Why
algebra. Basic algebra. It's
Like
something
a
more than,
Like a vector field of.
no. This is module is a ring with additional multiplication actually.
Think about the FL happen.
All right, but anyway, now here we are,
The blue one is
this one.
the blue. What is it? I think this one, yeah. This one, yeah.
Yes, okay. Now, we are going to define one more operation on XM. This what? Set of vector fields. Up to now, we know that it is a module on C infinity M. Now, take X, Y, two vector fields in XM and define the bracket. That's called Lie bracket of two smooth vector fields. In language of algebra, that is also called as commutator of two vector fields. You have two vector fields. You define the bracket of these two vector fields defined by this. And what is that? That is a smooth function. it is easy to show that this satisfies those two properties. That is, you can show that and also the derivation. So what do we see? We see that is also a vector field. You started with two vector fields and you define the bracket of them to be again a vector field. That is, you have defined an additional product on the set of vector fields, which was only module. Now, what happens? You have Lie bracket of two vector fields. And this Lie bracket satisfies the properties given in lemma 17. If you have three vector fields, x, y, z, and two real numbers a, b, and two smooth functions f, g, and infinity, then the bracket, first it is q symmetric. That is xy equal to minus of yx. And as a result, what happens? Xx should be 0. Second, it's linear in first lot if a and b are real numbers. And x of y plus z is also that linearity is there in condition 3. Condition 4, it is not linear over functions. That is, if you multiply it by two functions, fx and gy, find the Lie bracket fg xy, and you have two additional terms. And then you have the Jacobi identity. That is Lie bracket of x, Lie bracket yz plus y, zx plus z, xy 0. This is called Jacobi identity.
First condition. Here, maybe there are equivalents between xy equal to minus yx and xx equal to 0 for all x.
They are equivalent. They are,
Equivalent.
yes, it should be this. They are
Or
equivalent.
equivalent.
Yes. Now, this is a requirement.
It's for hard to prove.
They are very easy, straightforward.
Number
Maybe
four.
that could be done to meet some.
Yes, it is straightforward. What you need to do simply is this.
Just apply your definition.
Yeah, operate this on a function and expand, all cancel. All straightforward.
Yeah, by your definition number 2.
I saw the
Property number 2, not here.
Yes. Yeah. Yes, not the first part of definition. First part is, but most operational is the second equivalent part. Yes. Now, because this,
from this third result is we can deduce from the first one and this one from linearity with respect to the first variable and from antisymetry we can deduce three.
no, here they are real numbers,
Yes, yes.
but here they are smooth functions.
No, I mean properties 3 can be reduced from 1 and 2. Yes.
Yes, yes. But the best way is the following. What you do, you operate this on some function h. Operate it on some function h and expand using the definition. Then you will see all these things operating on h. For all h, so remove h and you get this identity. All right? They are straightforward, anybody can verify it. So what we have seen that this XM has additional multiplication of vector fields that is a bracket operation, satisfying those properties. This makes set of vector fields Lie algebra. What it makes it? So this XM is called Lie algebra of smooth vector fields or for a manifold. Yes, please.
But in general, maybe without condition 4, we can use that as a Lie algebra. Maybe
Lie algebra.
condition 4 is not necessary for the algebra.
Lie algebra requires only these two.
By the linearity and
Yes. Yes.
Jacobi.
Yeah, but these are the property. I have some question. Yes. I'm sorry, can you repeat it louder? Is there a relation between Lie bracket and inner product? No, nothing. No, their inner product is just on a vector space. Here, we are doing smooth analysis sort of thing. There is no, yeah.
But in general, Lie bracket is an algebraic notion.
Of course.
But inner product is something analytic.
Inner product is also an algebraic first, later on analysis too. It's basically inner product space, it's algebraic thing, yes.
What's the structure of the Lie algebra? Because this is my first time I see this function. What's the structure?
Say again, please. I'm sorry.
What's the definition of a Lie algebra?
Lie algebra is a module on which a module has only addition, right? And scalar multiplication. In addition to that, there is a product, extra product, satisfying those two conditions, Lie conditions. That is A dot A is 0, like that XX is 0, and the Jacobi identity. And of course, linearity. Then that module is called Lie algebra. Algebra. Basically, algebra with additional product, algebra becomes Lie algebra if it satisfies those two Lie conditions. That is A squared is 0, that is X dot X is 0, and this Lie at the Jacobi identity. Right?
في ذلك ولا؟
I don't ask about the Lie algebra. I ask about the Lie bracket. This one, what's the structure? X, Y between the square.
What's the definition of Lie bracket?
شو بنية إيش يعني إيش
Here we define here.
نعم كذلك كيف؟ ثلاث تاخذ تو سموث
تسوي فيهم تضربهم مثلا ولا إيش
لا هو دالة بالشكل هذا. You know, Sharif,
Yes.
their problem is YF. That's why they don't understand YF.
Why?
This definition, they don't understand what's the meaning of YF, this action. Why
Doctor, I think that they need examples.
We
Oh.
give example.
I give example. Now, look, I first explained, given a vector field, it acts on smooth function to produce a smooth function. Y is a vector field, YF is also a vector field. XF is also, YF is a smooth function, XF is a smooth function. X again operates on that smooth function, Y again operates on this function, smooth function. This difference is this. How it is defined. هذا معنى الموضوع من اليسار اليسار نسميها ضغط مجال، إذا الضغط اليمين نسميها رايت مجال.
اللي عندنا left module or right module. There is nothing called module. هذه الفكرة الموديل. لأن لو كان هذه الاكس ام هذه موديل، لأن من خلالها عرف اللي براكتس عرفته وقال إن في الجبرا. ايش معنى في الجبرا؟ إذا هو موديل with two properties اللي هو كتبهم number 1 and number 5.
It makes it Lie algebra. So for us now, the set of vector fields is a Lie algebra called Lie algebra of vector fields on a smooth manifold. So up to now, we have seen that it is this. Now,
دكتور excuse me. لما 17
لما 17
لما 17
lemma 17.
bracket is given with respect to first and second variable. Yes.
Say again?
Bracket is given with respect to first and second variable.
This is bilinearity, he said.
Linearity. Why you wrote that?
Yes, of course.
Property 3 additivity. It is linear with respect to
It's bilinear from here itself,
linear.
with respect to reals, but only with respect to real. When you introduce functions, its linearity is lost. You have that. So in lemma, it's not definition, it's lemma. It's describing properties of brackets.
But why you write the property 3? Property 3 is clear from the context from 1, from 2.
Yes, 1 and 2 into yes, yes. It is listed. It is redundant, you can say. It is redundant. Okay. Okay. And as you have seen, vector field, because constants are also smooth functions, like tangent vector operating constant is 0, vector field operating on constant is also 0.
Sharif, sorry, I have a naive question. I know it is wrong, but
Go ahead, go ahead. The purpose is that, not finishing.
purpose is to ask the wrong question.
Yes, it is always, you are right, yes.
Is it important to have to just stick with smooth functions to operate this smooth vector field on smooth functions, or we can just see one?
Then therefore C1 vector field. Actually, we are doing smooth from beginning.
I know.
Even manifolds can be C1 manifold.
Yeah, but if I take C1, what should be the next?
C1. Cannot be. Yes.
Also,
Okay.
C1, C1.
Yes, I mean, in general, in books of analysis, you will see that they don't talk about smooth manifolds. They talk about CK manifolds. That's manifolds of class CK and CK vector fields and all that. But we are doing differential geometry where everything is smooth. Where everything is smooth. Even you have serial. And you know that carrying the comb requires sort of continuous vector field. You have defined, you have their index of vector fields and all that. All that topology, it's of a differential topology. They're only continuous vector fields. Yes, please, whatever you feel, because the discussion makes things more clear. Now, a very important notion is this now. That is integral curves of the vector field. By the way, if this is a chart with local coordinates, then you know that del by del xi, they are smooth vector fields on U. Coordinate vector fields. They are called what? Coordinate vector fields. And because we are doing smooth things, cross partial derivatives are equal, right? And therefore, what will happen? Bracket will be always what?
If E doesn't equal G,
Sorry?
whatever I and J,
Yes. Okay.
because you said X in bracket X and X.
Now, and also what? Given any vector field restricted to charge. Yes, please.
This is the example in C1, for C1 vector field. It's I, it's G equal to the bracket equal to 0 for function in C1. Is it true?
No, it's not, because you
C1
are
no.
you need C2 at least.
At least second.
Yes. Now, any vector field restricted to the chart, neighborhood chart, will be equal to this is obvious. Now we are going to introduce a very important concept, that is integral. Suppose we have a vector field. On this manifold, we have taken this vector field. Take a point here. And suppose we have the curve. A smooth curve. Passing through point P. Then at each point, you have tangent vector that is called rho dot P. Restrict the vector field to the curve. If this turns out to be the tangent vector of that curve for all T, that is vector field restricted to, because vector field is defined globally everywhere on M. Therefore, it is defined along curve. The value of vector field at the curve, if it turns out to be the tangent vector of that curve, then we say rho T is an integral curve. Passing through T. This is the definition 21.
Oh, but this definition looks like sigma is an equation, right? As one can see from the definition, right? This sigma t is an equation, right? Is a solution to some equation.
Some differential equation, certainly. Certainly, it will be solution of some differential equation. Initial value problem indeed, yes,
Sigma is unique, must be unique.
not globally.
Up to some.
I'm coming to that, inshallah. Here is an example, an easy example. One can read the example, and you will see that if you can see the things properly, you will get the notion. Here I took a vector field in R2 and circle I took in R2. I found the tangent vector to this, it turns out to be this. And if I take the restriction of this to the circle, you will see that they coincide. They coincide, and therefore, this is an integral curve of that vector field. Any question?
Just if you make it a little bit bigger. No, no, not that much.
Too much.
No, not,
Not good?
Yes.
yeah, sorry.
Should I work it out?
No. It's
Okay. This is an example, but we can derive the differential equation of an integral curve. Be an integral curve. Passing through. Now what we do, can you bring water bottle for me also? Thank you. Okay, thank you. This is an integral curve of this vector field. I'm interested in seeing differential equation for integral curve. What we do, we take a chart around it. Because in manifold, you have always charts at each point. And suppose the local coordinates are x1, xn. So now what happens is that x know that x is some fi. What are these fi's? Are nothing but x acting on xi. Right? So x of rho t will be equal to and you know that tangent vector of the curve is given by now equate this component and we get equal to fi at t, sigma t, I will write t, where these xi's are nothing but xi of rho t. And fit is nothing but this. And subject to the condition that xi p, and this is subject to the condition that xi at t naught is equal to xi. This is the system of initial, this is an initial value problem for system of differential equation. These are the differential equations for an integral curve. If you want to, given a vector field, if you want to find the integral curve passing through this point, we need to solve this different system of differential equations. Here, this what I just said is here. Now, here is an example. I give you an example. Find, you are given a vector field on S2. This is S2. I'm taking the manifold to the S2 at this point on S2, and I'm taking a vector field, which with respect to this chart is this, where U is this coordinate neighborhood, upper half hemisphere, and the chart map is given by this. And therefore, the inverse of that is given by this. Then you see that that system of differential equation is, because it is two-dimensional, dx1 by dt will be here 1, and dx2 by dt will be minus x1. And subject to the initial condition, x1 at 0 will be this, and x2 of 0 is because this is xy, so it is 0. If we solve this system of equations, first equation gives you x1 equal to t plus square root 2, and second x2 t is found as minus half t squared minus 1 over square root 2. And therefore, the integral curve sigma t is given by, because x1 t and x2 t are from R2. From R2, you have to come back onto the sphere via this map, via that chart map, via this map. Phi inverse uv is this. So you found the solution on R2 coming back on sphere. That will be phi inverse of your sigma t will be phi inverse of x1 xt x2 t, and you find that you found the integral curve. So you solve the system of equations. You found the integral curve of that given vector field passing through the given point. Then there are two exercises. The first exercise, you are given two vector fields. X is y over del by del x, and y equal to del by del x plus x del by del y. These are two smooth vector fields on R2. Then the first part of the exercise is asked to find the Lie bracket of these two vector fields, x, y. Using that lemma, you can find the Lie bracket of x, y. And after you find Lie bracket of x, y, using the technique explained here, you have to find the integral curve of Lie bracket. Please solve exercise 1. If you have questions in that, it will be a pleasure to answer. Second is, you are given three vector fields again on R3. X is that, Y is that, Z is that. And just to appreciate whether I understood the concept well, the exercise 2 helps you compute Lie bracket of X, again Lie bracket YZ. First find the Lie bracket of YZ, and then find the Lie bracket X, YZ. And then there is theorem 23. Professor Abdurrahman asked a question about uniqueness that is answered in this theorem. If you have two interval pairs, sigma and rho, of the shape, such that sigma 0 is same as rho 0, say some point B, then what happens is that cannot happen at simply one point. When there exists a small interval, there exists a small interval on which they coincide. That is local uniqueness of integral pairs. That is this theorem 23. Have any question, please? And again, the uniqueness is derived through what? Through the existence theorem of differential equations. Suppose this is a smooth curve in the manifold, and you define x from I to Tn. Such that you have a smooth curve and you are defining such that x of t belongs to t of sigma t. And we call this as a vector field along curve. This x need not be defined globally on M, just defined along the curve. Only requirement is that at each point it matches the point to the corresponding tangent in the tangent space. Now, so we denote by this notation sigma the set of all vector fields along this. Example, tangent vector of a curve is a vector field along the curve. Given any the next definition is the following. If you have a smooth map, and if you take a vector field here and a vector field on M, you have chosen a vector field here and a vector field here. You say this vector field y is F related to X. If what happens is a smoothness. If what happens, df of X should be equal to y circle. Then you say that this vector field is F related to this vector field. And what happens, this F related thing respects Lie bracket. That is, if you have a smooth map from manifold M to N, and if you have two vector fields on M, two vector fields on N, such that their y1 is f related to x1 and y2 is f related to x2, then the Lie bracket of y1, y2 is f related to x1, x2. This notion we will require in future. That's why it is.
Sorry, maybe I missed something. What's the composition here? What's the meaning of that composition?
Why the map? Why circle? Because this will operate at a point of manifold. This will operate at the point of manifold.
So from M to N.
Yes. So it has to operate on the manifold N. So you need F here. In other words, what happens is this: DFP XP equal to Y of F. A tangent space level. Why you need this?
Because, yeah, and then that will be on TFT N.
Yes. For that reason you need it here. All right? Good. Next. If you have diffeomorphism, F as well as F inverse, both are smooth. Then
F is smooth and F minus 1 is smooth.
both are smooth.
يعني C infinity diffeomorphism.
Yes.
In that case, we say
Yes.
this.
Now, given a diffeomorphism between two manifolds, you get the map on Lie algebra of M to Lie algebra of N, and that map is defined by this: phi of x equal to d of x circle F inverse. Right? Then this map is Lie algebra isomorphism. That is, that map respects the Lie algebraic structure or preserves the Lie algebraic structures and behaves well with the Lie algebraic structures of xm and xn. Is that clear? That is, bracket is also respected and other operations are respected. All right, you have some questions? No? Good. So diffeomorphism is a very strong notion. Whatever happens here, of course, as long as we are dealing with smooth things, the same thing will happen there. Almost, right? But not the geometric structures. Diffeomorphism only preserve the smooth structures. Similarly, if F is a diffeomorphism, then that induces opposite side, C infinity N to C infinity M. This is the reason one is covariant and the other is contravariant. If F is a smooth map from M to N, why Lie algebra isomorphism is on the same direction. But when it comes to rings, that is ring of smooth functions, it is in opposite direction. If F is a diffeomorphism, then you have induced ring isomorphism, F star, from C infinity N to C infinity N, and definition is there. It's clear? So once you have diffeomorphism, it gives you isomorphism of Lie algebra to Lie algebra. And also it pulls back through isomorphism of ring to ring, right? Is that clear? Now we are going to slowly, we are developing. We first studied tangent vector, tangent space, tangent bundle. We introduced vector fields. And set of vector fields, we have seen that it has a beautiful structure, that is the algebraic structure. And now we are going to unlock one more beautiful thing about vector field, and that requires the group of diffeomorphisms. Suppose M is an n-dimensional smooth manifold. We write dm. What is dm? M is different. We are collecting all diffeomorphisms of a smooth manifold. Very large set, collecting all. It's not amplified. At least we know what is that? Identity. Right? But it's very, very large set. If you want to make it manifold, it becomes infinite dimensional manifold. Very large set. And one more thing. Once F belongs to Dm, F inverse is also in Dm, right? And we define an operation for Fg in Dm. We define the product. F dot G to G circle with respect to this product, because identity is there. For every element, inverse is there. This product makes that set group. But it makes it group. It's very large group. And it is called group of diffeomorphisms of M. What is it? Yes. 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 But it's a smooth map from M to M, such that inverse is also smooth. We took Fg in Dm means both are from M to M. Maybe I didn't understand your question. Another manifold. No, that is different thing. Here, we don't have the composition there. Here, you are fixing manifold. Group of diffeomorphisms of M.
Here we can speak about C1 diffeomorphism, C2, CK diffeomorphism.
Say again?
Here, in your definition, we require only diffeomorphism. And we can speak about C alternative diffeomorphism.
There are CK, C1 diffeomorphism also. C1. I mean, but we are doing smooth, so it's where we can see.
سموث سي ام بي هم من يبداوا من نهار يحكوا سموث على سي ام بي.
No, I think smooth does not mean C infinity. Smooth means
No,
it
no, no.
satisfies what we need.
No, smooth means C infinity. No,
Yeah,
smooth means C infinity.
actually, this concern is all the notions I have defined. They hold for even C1 except even. exactly that, but there you need C2. But all, even tangent bundle. But tangent bundle requires at least C2 because other coordinates are coming from differential, right? So see here in the smooth manifold, everything is smooth, right? And that makes life interesting and easy.
And it's not needed to talk about C1 or C2
Yes.
manifolds unless if you need it. Just
Yes.
stick
And-
with smooth manifolds.
Yes,
And
you're right.
that's better for research.
Now we have defined the group of diffeomorphism. As I said, smooth vector field we have defined in two ways. Now we are going to show that every smooth vector field, there is one parameter subgroup of group of diffeomorphism. Given one vector field, there corresponds one parameter subgroup. Now, what is that? First, let me explain the definition. Suppose M is a smooth manifold. Then one parameter group of transformation, in some books, they are also called flow, global flow. What is called? Global flow. One parameter group of transformations is a map from R cross M to M. It's a smooth map. You know, R is one-dimensional manifold. M is n-dimensional manifold. This is M plus n plus one dimensional manifold. And how is defined? Phi of TP is phi TP. Collection of this, what you do is you take phi T what you are doing, you have dm, you are, for each t, you are taking a diffeomorphism from M to M, phi t. What is it? A sort of a curve, smooth curve. Right? So this is one parameter. Is a diffeomorphism. We ask it respects the group structure of R. That is phi of T plus S is phi T circled with phi S for all.
Group.
Can be divided by one element.
No, you require a curve, smooth curve, all of that infinite dimensional manifold, right? So phi T is a one parameter family of diffeomorphisms, which respects group addition. I mean, group structure of R is T plus S and phi T sacrifice. This is composition this is a composition in Bm. This T plus S is a composition in R. That is, it is additive homomorph. What is it? Group homomorph. And also one more requirement. At 0, it should give the identity map, which was the first diffeomorphism we discovered. So this family of diffeomorphisms is called one parameter family, one parameter group of transformations. One parameter group of transformations. What is it? Phi T is a subgroup of group of diffeomorphisms parameterized by T, right? That is that. This is the homomorphism. This T going to phi T is a homomorphism, and there phi 0 we want it to be identity, right? So by one parameter group of transformation or a global flow phi T, we need collection one parameter family of diffeomorphisms of M satisfy that fire P plus S should 5P7. 5 0 should be. R1 power. Yes, please.
How is it related to the integral of
That we are coming now. As I said to you, no, and that's a good quality in you. As long as we are impatient, we learn.
For example, the group of people who have received this one color. If the new color is the
Oh, okay, good. So this is very good. Very, very good.
very good.
See, the biggest is, set of homeomorphisms. This is part of it, but still very good.
Can you explain some family of this?
Yes, we are coming to that. We are coming to that.
I wrote something. We wrote some nice things. But it is known by, I forgot his name. I think it's talking about this, this is not as important. Just a moment. It's known just 70, 60 years ago.
Yeah, somebody asked him, what is your religion? He said, if you want. The famous geometer who wrote 6 volumes, Spielberg.
Yes.
Spielberg. Yes. SubhanAllah.
Yeah,
So now, I'll take 1 minute, just a little water I need.
I don't know who Edward and is same to you.
Is
Yeah.
actually
The hero.
differential equation, differential is so close. And these 3, 4 people is then
Cross. Double E and
Hamilton. These people, actually, if you read the proof of Poincaré conjecture, you will be so amused that the Poincaré conjecture was more than a century-old open problem, showing that a compact 3-dimensional smooth manifold without boundary must be diffeomorphic to S3. Must be diffeomorphic. The proof of this around 400 pages. Proved by ultimately.
Yeah, there are many books.
Yes, proved by a Russian mathematician who was known to be not normal. And then, of course, he did an abnormal job, right? So, yeah, Pellerman. He did not go for receiving the French medal. You know that?
Yeah,
Yes,
because he has some
No. Also on the middle
political
field.
problem.
Not only politics. These people are not normal people. They do abnormal things. I mean, and actually, do you know how many subjects interacted together?
All that.
All math. What to talk of that? Fermat conjecture. The number theory.
And it has geometry and topology.
It was not settled in algebra. It has to differential geometry, algebra, geometry, differential topology, all that came together.
That's important to tell everybody to know all mathematics.
Yeah.
You will not know all mathematics, but try to learn as much as we can.
Yeah, look, what happens is, we are human beings, of course, we cannot know all the things. But we know, for example, I was not knowing how to run that computer. But now I learned what I need. So this is how also you expand in mathematics. You go on expanding your, I mean, it is crime to say, analyst, I can't talk about it. It's a crime.
Yeah, unfortunately, it happens like
Yeah. So have intersection. We have to, of course, you cannot be master of everything. Even Bellarmine is not master of everything, but whatever he needed, and the breakthroughs come through hybridization, intersection of two notions.
And that's why at that age, at that time, I think it's 70, they started talking about global analysis when James Lee wrote something, but now it's stopped.
No, it's still, for example,
Global analysis has geometry and analysis.
yes,
So
the Rishi flow, for example. Do you know what is happening now in Rishi flow? There is a, not very old, 5-6 year before, there is a paper, application of Rishi flow to the surgery of the. You know, before, if there is a tumor in brain, they used to take section directly. Because of that, 40 to 50% patients used to lose some of organs. Then the paper using Rishi flow, they proved that you should take the section through the flow lines, through the geodesics. And once they adopted this, now there is no damage.
But they applied the shrimp. I don't know how they find the geodesics in the brain.
It's a
They
brain
cannot see.
manifold. Brain is, by the way, smooth manifold. There are no corners. Subhanallah. If you want, I can send you that paper. I have that.
Yeah, please.
That surgeon.
So it's a good research.
Yes. And there is a lot of interaction. Not only that, you know,
But Professor, you want to advise the students?
I would advise them
No,
that it is a crime to say that I'm a student of Java, I don't need analysis. Then it's a crime.
Yeah, you will be dead immediately.
Of course, no. Yeah. And if somebody are saying that your analysis, you don't need geometry, it's a crime. We need all basic things. We need to learn them.
Yeah.
And it's not necessary that you become expert in other areas, but you should know. For example, I know how to use the computer. That much I need, I should.
Yeah, but if you want to advise them by how to,
It's not difficult.
no, how to, because I promised them to, that you will give them some advice on how to write a research proposal, but maybe not now you can answer because the time has already finished, so we have a break. But they are waiting for you to give them advice on how to write research proposal, inshallah.
Just a rough sketch.
انتبهوا ترى عن
Suppose, for example, in which area you are going to, what is your area of specialization?
for example,
Analysis, right? Now, in analysis, what you need to do, first thing,
shall you use the microphone because they are going close to it.
oh,
ترى عن مشاريع.
but I have to finish first this.
We finished with it.
No, not yet.
No, we delay this till tomorrow, but this is because our time has finished.
My intention was to finish this whole thing today.
Inshallah, you will.
Inshallah. Yeah, actually, for example, you are going to do analysis. Then what a good student should do is he should search eminent mathematicians in that field and his recent research. And
ترون الدكتور اللي تعرفون ابحاثه متميز يتفقون في عمله بالمسمى هذا تنتبهوا.
for example, الوردي was yours. الوردي, right? He's also an eminent person. Or that person who settled point and conjecture came from UK, what was his name? Sorry, not point and conjecture. Farmer's last year. What was it?
Martin Hayren?
لا هذا قديم هذا كلمة كثيرة.
قديم.
Yeah, I'm forgetting his name. Okay, there are prominent, choose some very good universities like Oxford, Cambridge, right? Or Princeton.
This is very important because I know students from anywhere. They just see that a person graduated from a very bad university, which has very bad fame, and they choose because that person graduated, I should be graduated, and they go to that university. That is very big disease.
Yeah. So choose from very good school, a good mathematician. Search his recent paper. Search his paper appeared in